This is video 8 for Computer Science 2124, also known as the ongoing saga of linked list design. I rather ominously said last time that for the remove operation was going to require us to summon all of our toolbox of all the things we know about classes and all. It's not that bad. Remove. Remove. Take a node out of the list. Well, of course, we'll always take the first node in the list. No, not that empty head node. I mean the first real. No, let's see. We don't even want to do that either. Maybe we should take the last node in. Oh, maybe we should take one out of the middle of the list. You see where I'm heading with this? We're going to use that cursor again. It's going to be our bookmark to keep up with where something of interest is about to happen in the list. And I'm going to introduce the idea of a precondition. Big word, simple idea. Precondition, the precondition for remove. Cursor points at the node in the list. Any node I talk about is in the list. Cursor points at the node that precedes. Precedes the victim. In case that's not crystal clear, here's a fig, a picture. It's not before and after. It's just the cursor points at this node, which holds its arbitrary position in the list, S, which points at T. There. Cursor points at node that precedes the victim, T. T, bless your heart, you're not long for this world. You're about to get removed, about to get whacked. You might be asking the question, you might, if the cursor points at the position of interest, why not go ahead and just delete the cursor node and leave T alone? Well, think about this. To be able to do that, we're going to have to know this node back here. And we don't have a pointer to that node back there. That could be the 19th node in the list. It could be the 27th node in the list. Don't know, don't care. But we're making it easy on ourselves. It's going to be fairly easy. Let me put another node there here. STU. It's going to be relatively easy in terms of the pointer manipulation to delete T. All we got to do is bypass it. We'll perform a little surgical bypass here on the list. So we just make S point to U instead of pointing to T and free up the storage at T and done and done. It doesn't involve anything back here. Doesn't involve anything over there. Good, nice little order one operation. Now, that's my precondition. And of course, a precondition, that's exactly the same as class invariant. Oh no, it is not a precondition. This is something, STHG, something the caller is responsible for. Fortunately, these are not English lectures, so I can end with a preposition if I want to. Something the caller is responsible for. The caller is responsible for setting our preconditions. They don't know anything about class invariance. The main program is blissfully unaware of any class invariance. Those are rules that we use to govern ourselves as the linked list designers, the member function designers. Precondition, though, the caller decides, you know what? I'm kind of tired of that first node in the list. I think I'll remove that. So it can call move to front, which we provided as an operation. It can call move, move, move as many times as it wants to and control whether it deletes the third node or the last node or the middle node or whatever. So it has the power and the authority to do so by using our cursor movement operations. And it takes that responsibility off us. We don't have to try to figure out what the hey, the main program's trying to do. We just go ahead and as long as they've called remove correctly, then we'll just take out the node after the cursor node. That's all we need to know about what's going on. Kind of, sort of. There's some stuff we're going to have to check. I've got a space. That's the end of the precondition. Here's a before picture. Generally speaking. Head points way over here somewhere. Empty head node, yada, yada, yada. I'll stick with the, no, I'll change those. That would be confusing. V, W, X, yada, yada, yada. And I'm going to point the cursor here, just so it's easy to figure out what should happen. What should happen is a W should get whacked. So the actor picture, if it got space for that, head, have to make it smaller, sorry about that. Head points at yada, 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 and it still points at V. We didn't disturb node V. And the cursor still points at node V. Why? Because there is nothing compelling the cursor to move as part of a remove operation. The remove operation is charged with get rid of the node after the cursor node. That's it. Don't change anything else. Don't move the head pointer. Don't move the cursor. Don't do anything like that. So this will point at node X. Barely have room. And X points at who knows what, don't know, don't care. So that's what we got. And we just got to dive in, I guess. Let's see. We want V to point to X. So here's our steps. If I want V to point to X, somehow or another I got to get a hold of this pointer right here. If you look at that, that's cursor, arrow, next, arrow, next. Take cursor, arrow, next, and put it into cursor, arrow, next to make it point to X. Set, that's a long statement. Cursor, arrow, next, to cursor, arrow, next. I got that backwards. You caught me. Set cursor, arrow, next. I'm changing this. Bypass the point to X. Set cursor, arrow, next. I'll have to go back and double check this against the picture. Good thing I have a picture. Set cursor, arrow, next. Do cursor, arrow, next, arrow, next. Now, this assignment, first of all, we need to track this down. Cursor, arrow, next, arrow, next. And there we are. This is the address of node with X in it. Take the address of node with X in it and put it in cursor, arrow, next. Cursor, arrow, next. So V will point at node X. What could be simpler? Well, it might be simple. It's not right. Make sure the ink's dry. Now draw a line through it. Why? Memory leak. We don't want W to go floating off out in space. We want them to be returned to the system. Go back where you came from. We got to be able to free up that storage. And if we start with this, we've lost node W and we cannot free up the storage. Is that? Yeah. So we better hang on to that. You know what? Set. We need a pointer. We need a pointer, a bookmark, put my finger on node W before we do the bypass operation. So I'm going to call it victim. Nice Gothic word. I'm wearing a black sweater. Set victim to cursor, arrow, next. Let me see if I get this one in the right order. Cursor, arrow, next is the address of node W. Take the address of node W and put that in victim. I'm going to switch color because I haven't done it in a long while. Because I'm butchering this picture and I might have to undo it and I want to see what new stuff I added. That's too light. One moment, please. Victim. I hope that's good enough. That's where we are so far. Victim pointer. Set victim to cursor, arrow, next. Now, pause and reflect for just a minute. All these decisions we have to make. Should victim, that's a fancy name, should that be a state variable? Or can we get away with a temporary variable? And the reason I phrased it that way, if we can get away with a temporary variable, we'll always choose that. We already got all this other stuff we got to keep up with. No more mouths to feed. Victim is just holding on to node W until we can get rid of it. And then we don't need the victim value anymore. So yes, victim will be a temporary variable. It's a local variable. I'm trying to learn to sneeze in my elbow. I'm used to sneezing in my hand. Where it's only a temporary variable inside the remove function. So set victim to cursor arrow next. And then now we can do that. Set cursor arrow next to cursor next. Doing the bypass operation. I think we can. I've got victim set to cursor arrow next. Check, done that. Now, find cursor arrow next, cursor arrow next, the address of node X. Put the address of node X into cursor arrow next. So that arrow's gone. We broke it, but that's okay. We put our finger on it with our victim temporary variable, and we're doing the bypass operation. Now, why did we need to hang on to the victim? So that we can delete the victim. I'm not putting dashes in front of all of them, so I won't put it in front of any of them. Delete victim. So, victim is gone. That's an X on top of that. I don't know why the other colors don't work on this whiteboard very well. It's just a fact of life. But this butchered picture, believe it or not, does look like the after picture now. The victim is gone. We even freed up the storage. And cursor arrow next closed up the gap. V can point to X. So, no problem. Is there? Remember, so many things to remember. Way back, we started looking at these pointers. I point to you, you point to them, they point to somebody else. The only one of those that's allowed to be 0 is the very last one. Otherwise, we risk the dreaded segmentation fault, the access violation. We've set ourselves up for that possibly here, if we're not careful. Look at this. We didn't test that. That's a string O pointers. The only one of those that could possibly be 0 without crashing the program is this one. What about this one? Cursor arrow next. Trout, no. Trout, no. Is there even the possibility that cursor arrow next could be 0? Yes. Cursor arrow next is 0 if cursor points at the last node in the list. What if X is actually, well, I'm not going to butcher this picture any further. Visualize this. If cursor arrow next is 0, cursor is pointing at the last node in the list. And what about our remove operation? It is not going to be successful. You can't remove a node that's not there. Cursor points at the last node in the list. Maybe V is the only thing there. Then that's a 0 pointer. You can't remove a node over here. It'll crash the program. I'm trying to actually do this assignment statement. And you're way ahead of me, I know. We can check. We can check and see whether or not there's anybody to get whacked. Right here. Set victim equal to cursor arrow next. Way back when I did that, set victim equal to cursor arrow next. If V had been the last node in the list, then what did I just now do here? I'll pause until you answer the question to yourself. If V had been the last node in the list, when I said victim to cursor arrow next, I just now set victim to 0. Look at this. I was even looking ahead. I left a line in between. There's the possibility this operation would fail. There's a possibility remove has no work to do if there is no victim, if there is nobody after the cursor node. If victim is 0, then return false. You gave me one job to do, but it was a bogus job, and I can't do it, so I'm going to return false to you. If victim is 0, then return false. Otherwise, we're still here. There is a victim, and we're going to set cursor next to cursor next and delete victim, which brings us back to this picture in the general case. Is that it? Could that be all there is to it? Well, unfortunately, no. Somebody got ignored here. Set victim to cursor next. Victim 0, get out. Delete victim. Return true. There. Now it's done. No, no, no. We're still ignoring the tail. Now, I'm sorry about this. I'm going to have to reclaim board space. We're still talking about remove. Remember, every time we add a state variable, we got to go back and rethink operations. So this is a brand new operation, not really any rethinking. I'm going to change the picture. Before picture, I didn't leave, I was thinking ahead a little bit. I wasn't thinking ahead a lot. We might have to squeeze some steps in between these steps down here. Here's that special case, those pesky special boundary conditions. Z, I'm going to resurrect Z. You know what about Z? It's the tail. Oh no, oh no. The remove operation is going to delete the last node in the list. Why does that affect the remove operation? Because if we get rid of the last node in the list, then this will be the new last node in the list. And we can't leave the tail pointer hanging out there. We can't let it point at the ghost of node Z, which will now be a garbage value. We don't want to set it to, well, not only do we not want to set it to 0, we're not allowed to set it to 0. Tail always has to point at the last node in the list. So I'm going to write that as a question. It's a boundary case, one of the special conditions to cover what if last node is the victim. Well, a silly two-part answer. What if the last node of this? One thing we got to do, we got to detect it. We got to know that this is the case before we do anything special for it. We got to, man, this is not an English class. We got to detect it. And we got to, I'll stick with my convention English here. We got to update the tail pointer. I am bound and determined to find some other color than black so I can squeeze stuff in between here. If victim is 0, no. If victim is 0, we're gone. If this is our before picture, let's see. How can we detect that this is the situation that we've got and we've got to fix it? Well, let's look and see what we got here. Cursor, arrow, next is tail. So the solution to 1 would be check if cursor, I hope you can read that, I'll read it. If cursor arrow next is tail, in other words, if cursor arrow next, that pointer and tail are both pointing at the same node, that means we do have this special case. That means our victim is the last node in the list, and we've got to update the tail pointer to, if that's true, what do we update the tail pointer? Looking into the future, also known as the after picture, after, head, cursor, tail. Head is a superstar over here, but it never does anything. Not really. Cursor, there's no reason to move the cursor. Still points at node V. But the tail node got whacked. That was our victim. Would have been more appropriate for V to be victim, huh? But the Z node is gone. So this is the new last node in the list. It'll have tail pointer 0. And the tail needs to point at the same node as the cursor. And I think I just answered our question. If cursor arrow next is tail in the before picture, then we need to update the tail pointer to be cursor. Set, you know what, I almost said set cursor to tail. Bad, professor. Set tail, that's the one we're updating. Set tail to cursor. Now let's see. Well, where do we do that? If cursor arrow next is tail. If cursor arrow next is tail, it means our victim is not 0, so we're down here somewhere. Set cursor next to cursor, arrow next, arrow next. You know what? I was doing that looking at the before picture without looking at any of these steps. So I'm going to say this asterisk right here, we can slip that in as soon as we know that we're still here. We can detect that we are about to delete the tail node before we actually even delete it. So there could be other places it'll go, but I think that'll be good enough. I'll leave it as an exercise for you to trace through this newly butchered Frankenstein-style algorithm for the remove and see if it works for all these special cases that we've described. But let's see here. Set victim to cursor arrow next. I'll just march through this one last time for old time's sake. Set victim to cursor arrow next. Victim. Cursor arrow next is node Z. Done. If victim is 0, return false. Victim is not 0, so we're still here. Here come the asterisk steps. If cursor arrow next is tail, let's look at this. Cursor arrow next is tail. Yeah, they're both pointing at Z. Set tail to cursor. So set tail so that it points at the cursor node rather than the last node. We're abandoning node Z. It's about to get whacked. Set tail to cursor and then pick up where we left off and see if the rest of this still works. Set cursor next to cursor next. Cursor arrow next. Arrow. Oh no! Cursor arrow next is 0. Cursor arrow next. You know what? Jimmy Crack Corn, and I don't care. The last variable in a sequence, a chain of pointers like that, that can be 0. That's okay. Sometimes it has to be 0. It's anything leading up to that can't be 0. So this is a 0 on the right-hand side, and I'm putting that into cursor arrow next. Cursor arrow next. So I'm changing that to a 0, which seems bizarre. It looks like I'm inviting memory leaks all over the place. Delete the victim. Victim, you are gone. And return true. Return true because we're done? Yikes. This was the special case where we deleted the last node in the list. Victim is going to go away. That's only a local variable. And even though it doesn't look like it, look what we got here. The head points at yada, 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 and then the cursor points at node V, which has got a 0 pointer because it's the new last node in the list, and the tail points at the new last node in the list, and everybody's happy and they go home. Return true. You wanted me to do it, and I did it. What do we have remaining? You know what? We got the destructor. For now, I'm going to leave this massive memory leak and do the destructor next time. See you online.